In Psychology Today article talking about grieving and grieving process, which is 4 stages: denial, anger, bargaining, despair, and acceptance. I think most of us now close to the final stage of accepting that this is happening. So what we need to do to pass through these difficult times? The answer is simple: stay positive and making sure that you are having a nice day every day, regardless what is happening in the future, what is happening tomorrow. Just make sure that your day is nice and cool enough for you to enjoy. So practicing this will decrease the feeling of uncertainty and worrying feeling. And if you can do also practice communication with people. So we are requested to practice a social distancing, but not social isolation. So connect with your friends, text them, call them. So this is will make you change the mood. Get some workout if you are into the workout. Do something creative, drawing, programming. Many websites offering great content during this difficult times. Look after others and share positive vibes, because happier the people around you, happier you are. So this is the safety moment for today. Okay, so as for the agenda, we will touch on the importance of high pressure, high temperature hydrocarbons production with the recent growing trend of gas reserves exploration and production. Then we will discuss the tool systems that we are using to address those challenges. Later on, we will go through some case studies where we have overcome the challenges of the heat and time. So we are pushing the limits of the heat and time, as we will show you in the next case studies. This slide is just a quick overview of what services SDI is offering to support the wellbore placement and productivity applications. We have been offering our services for more than 50 years and across 22 countries. SDI, Scientific Drilling International, supports oil and gas, geothermal, civil engineering markets by reliable, robust downhole technologies. In today's presentation, we will focus on the cased hole services product line and its high pressure, high temperature features. So in this slide, I thought to give you a quick insight of the world energy outlook, as this links directly to the subject of this presentation, high pressure, high temperature challenges. In PEP recent energy outlook published in 2019, it shows that the hydrocarbon will remain the major source of energy, with observable increase in the gas dependence as a primary source of cleaner energy. In the chart on the right, we can see the world consumption of natural gas has been growing since 80s, and we need more gas reserves to sustain that. So the operators are more willing to invest in exploring and developing more gas reserves. And on the chart on the left, the red bars are representing the gas demand, which will increase in the next 20 years. So we can see an increase from 2020 up to 2040. So we can see a significant increase in the gas demand and consumption as fuel. So both oil and gas will remain the primary source of energy. The reason of this slide that most of gas wells, probably not all of them or all of them, are exhibiting high pressure, high temperature downhole environment. So what makes a well classified as high pressure and high temperature? The term itself, high pressure, high temperature, may be applied to the wells that have only high pressure or only high temperature. Actually, few wells have both high pressure and high temperature. An interesting oil and gas industry study back in 2012 it estimated that around 100,000 of wells were drilled back then, and only 1.5% of these wells could be classified as high pressure, high temperature. Yes, relatively small in number, but these wells are often representing a significant resources and requires specialized equipment, proper training, and advanced planning to make it a successful intervention. So a well may be a high pressure. If we can look at this chart here on the left, so the well may be a high pressure, most likely due to the pore pressure. Okay, the pore pressure means the pressure of the fluids within the pores of the formation rocks. So pore pressure increase with the depth because formation must support. Pore pressure versus depth can change rapidly due to any geologic features in the formation, variable overburden forces, which is making the interval of this pressure is high, and we can classify this well as high pressure. The story here is different for the high temperature. As this mainly depends on the geothermal gradient. As you can see here, this is a group of geothermal gradients with respect to the depth and temperature. So we can see here that the average geothermal gradient is around 1.4 degree F per 100 feet. This is equivalent of 2.55 degrees C for 100 meters. So considering this gradient with this trend, we will reach to 350 degree F in around 19,000 feet, which is equivalent to 6,000 meters. But it's not a linear relationship as it looks like. So the downhole temperature may be influenced by external conditions such as hotspots, geologic features, and this can change the whole situation downhole. So we can have a higher temperature in much shallower interval. Actually, not only related to the geothermal gradient as well, for the thermal EOR, where we have steam injection. We have a high temperature downhole environment when we are applying steam injection as well. So this graphic provides a classification of high pressure, high temperature by the reservoir temperature and pressure. So we can consider a well classified as high pressure, high temperature if the pressure is greater than 10,000 psi and the temperature or the temperature is greater than 300 degree F. So this shaded area is representing different well types: oil producer, gas producer, geothermal well, steam injector, ultra deep offshore well. So that differs from each well to another, depends on the type. I thought to group the list of the applications that related to high pressure, high temperature, as you can see here. So we are seeing a growing demand for high pressure, high temperature technologies when it comes to the unconventional and frac treatment development. Even for the routine where surveillance for extended reach, for deep wells, there is also a growing demand for high pressure, high temperature production logging tools. So my colleague Riza, product line manager, he will walk you through the Vulcan family system, which we are using to address the high pressure, high temperature challenges we are discussing. Riza.
Yeah, thanks, Samir. Hello, everyone. It's very good to be here with you today. I'm sitting in Amsterdam, in the Netherlands. So we'll be going through a number of very interesting case studies, and they're all based on applications that we've used tools from the Vulcan family of logging tools. So that's the Vulcan FLS 1.44, 1.75, 2.25, and the MFT 24 caliper. To give you a greater insight into the Vulcan family of logging tools, this is a breakdown of the systems. So on the left, you have the production logging systems. The branch on the left is the memory system, which is the 1.44. On the right are the SRO and memory enabled systems, which are the Vulcan FLS 1.75 and 2.25. And the multi-finger calipers, they're all memory systems, and our oil field caliper is the Vulcan MFT 24. that's rated to 220 degrees C. The base PLT system consisting of gamma ray, CCL, and pressure temperature and spinner, that's rated to 315 degrees C. The Vulcan FLS 1.44 and the 1.75, they can both have tuning fork density and capacitance integrated into the system, but only in memory mode. And again, that's rated to 220 degrees C. So the figures against the 3 Vulcan FLS systems, they refer to the tool OD. And so the bigger the tool OD, the better the thermal insulation and the longer the potential downhole duration of the log. So the Vulcan FLS 2.25 offers the longest possible duration downhole. Okay, next slide, please. Yeah, I thought I'd start off with special with a very special case study. It's a relatively recent log. The operator wanted to obtain a conventional PLT from its gas producing well, but the challenge was the temperature and the amount of information that they sought to acquire from the single run. So the temperature was 194 degrees C, 381 degree F. That they wanted to obtain a flow profile, cross flow. They wanted to perform a multi-rate test for accurate SIP analysis, and that amounted to a run duration of 20 hours. And at a temperature of 194 degrees C, that was a big challenge indeed. But we were able to offer a fit-for-purpose solution to that challenge in the form of the Vulcan FLS 2.25. We were able to perform the log program as originally intended by the operator. So this consisted of shut-in passes, flowing passes at 2 different rates. Critical to the success of such an operation is the maintenance of the internal tool temperature below the temperature rating of the battery, as well as the electronics. And on this run, the internal temperature remains comfortably below the limit of the battery and the electronics. So the value that the customer gained from deploying the tool was that they were able to accomplish everything in a single run. That provided operational cost savings, and it eliminated an additional run, as well as minimizing production downtime. Okay.
Yeah. If you allow me, Riza, this case was also a very interesting case in the Middle East, and we have combined both high temperature technologies from the Vulcan families, the multi-finger caliber 24-arm high temperature, and the 1.75 high temperature BLT as well. So this was a pretty new completed well with 2 perforation zones, upper perf and lower perf. And the story of this well is a pretty interesting one. We have run the BLT, and then we found that the upper perforation is contributing, and there is a big question mark about the lower perforation because it's not contributing as we can see. So Riza will walk you through the solutions and the sequence of procedures that we have followed to address this challenge.
Yes, so as you can see that we have a log plot of the MPLT data. So the first thing that the operator sought to understand was the productivity of the 2 perforated zones, and they were particularly interested in assessing the presence of any crossflow. So to do that, we performed passes in the shut-in condition, and the spinner response on the two tracks on the right clearly indicate the presence of crossflow, but across the upper perforated zone. They were expecting for there to be crossflow between the upper perforated zone and the lower zone, because the lower zone was particularly high pressure. But as we can see in the spinner response, the crossflow appears to be limited to the upper zone alone. We do see a response in the temperature curve across the lower zone, which does seem to indicate some form of fluid entry, but the rate wasn't sufficiently high for the spinner to detect it. So the MPLT provided some answers to the operators' uncertainties about the productivity of the two zones, but it didn't provide all the answers. So the next consideration was the status of the perforations, whether or not the liner was perforated as expected, and to help them with that objective, they wanted to run a multi-finger caliper, and at that temperature, our caliper was the only viable option. So as you can see in the video, both zones were in fact perforated as planned. Spiral phasing has been captured by the caliper. So that provided another answer to their in their investigation of the productivity of the lower zone in particular, but it didn't provide them the answer as to why the zone wasn't as productive as hoped for. So subsequent to the logging that we performed and the data that we provided them, they were able to take further steps in stimulating the low zone, and they were in fact able to stimulate that zone and significantly add to the well's productivity and bring it online very economically.
So this is another case with different applications where we have used our high temperature multi-finger caliper as well. And this time it was for one of the steam injectors in the Middle East, and the whole field was applying a thermal EUR applications and injecting steam in vertical steam wells 24 hours, 7 days a week, 365 days a year. So it was challenging to perform a routine well integrity surveillance for these steam injectors due to the high temperature downhole, and also the available technology to deploy a multi-finger caliper. So you can imagine that for every caliper, the operator is required to pump cold water to cool down the well to be able to deploy low temperature multi-finger caliper. So Riza, if you can walk us through the case study as well.
Yeah, sure. So in this case, the operator didn't have the option of quenching the well to run a conventional multi-finger caliper. And again, for that reason, the only viable option was our multi-finger caliper rated to 220 degrees C. However, the bottom hole temperature remained uncertain prior to the log, and to mitigate to mitigate the risk of the bottom hole temperature exceeding the rating of the caliper, what we decided to do was to run our Vulcan FLS 1.75 system in surface readout mode above the caliper in order to monitor the downhole temperature real time. We found that the maximum temperature was 208 degrees C, 407 degrees F, and the log was the caliper was log was performed as planned. We didn't need to take any shortcuts. We were able to log at the conventional speed at 10 meters per minute. So that meant that the data acquisition was maximized. Another challenge was the completion. We had to log 3.5-inch tubing as well as 7-inch casing in one run. And another factor was the minimum completion ID of 2.25 inches. But with a tool OD of 1.85 inches and a measuring range of 1.85 to 7.2 inches, we were able to perform log the entire well in one run. So as you can see in the video, significant pipe deformation was detected. I guess you can classify it as classic helical buckling and an obvious result of long-term sustained steam injection.
Yeah. Okay. So this case study is also related to the well integrity applications related to a gas producers or oil producer. We can see leak detection in oil wells or gas wells. The life is easier when the temperature downhole is a standard. So we can use the available technology in the market, but it gets more difficult when we are required to identify a leak in high pressure, high temperature well, because we are challenged by the procedures, the lengthy procedures we would like to perform to pick the leak, and the bottom hole temperature as well. So this case study is highlighting one of the leak detection cases that we have addressed using the 1.75.
Yes, so at the time this log was performed, the operator didn't have access to a high temperature spectral noise logging tool, which would be run for such applications. But we were able to offer an alternative solution in the Vulcan FLS 1.75. So the sensors that were run included gamma CCL, pressure, temperature, and spinner. What we see in the middle track in red is the temperature response. So the solid curve is the down pass and the broken curve is the up pass. Now the difference between the two is because the down pass was run in the static condition, but prior to starting the up pass, the well condition was manipulated so as to encourage flow across the leak path, and that's the reason for the delta in the temperature. So as indicated, there's a significant cooling effect. It was a cooling effect because this was a relatively high pressure well, but it was a cooling effect because the source of gas was less than 450 bar, which created a Joule-Thomson cooling. But if it were higher than 450 bar, then a reverse Joule-Thomson would have been observed. So just to confirm that that the leak was in fact in the outer 9 7/8 casing and not inside the production tubing. We can see the spinner response not responding at where we see the cooling signature in the temperature. So that confirmed that there was no leak in the tubing, but in the outer casing. So this was an offshore, high-profile North Sea well, but we were able to perform the logging on slickline, which which brings cost savings and also improves the HSE risk factor quite considerably.
This is another case using high temperature 1.75 system, but this one is more challenging because the logging procedure itself, it requires to stay downhole for a longer duration, as we require to record 6 hours of build-up data, and this has made up the total run duration up to 20 hours. Downhole temperature is 186 degrees C, and there is interesting finding that one of the perforation zones is contributing, the lower one is not. So Riza will also highlight what technology we have used in this case as well.
Yes, so again, the operator was looking for a conventional PLT to obtain information on the production performance and reservoir properties. They needed fluid ID sensors. So we deployed the Vulcan FLS 1.75 with TFT and capacitance. On the plot here, from left to right, we have spinner, temperature, pressure, tuning fork density, and capacitance. So where indicated, we see clear evidence of fluid entries, both in the response of the TFT and the capacitance. Just above the bottom perforated zone, we see a significant cooling signature in the temperature response, and the density deflects towards gas values. Now, but the spinner is unresponsive. So this was interpreted as being a gas jetting phenomenon, whereby the formation pressure is considerably higher than the borehole pressure. So the gas, there's a gas jetting effect into the static column of water. So that's why we're seeing a significant response in the temperature and density, but the rate wasn't high enough for the spinner to respond as well. So again, a very challenging application. 20 hours, it's 186 degrees C. When you're running fluid ID sensors as well, is a big hurdle. But our system is tried and tested, and we were confident that we would be able to meet the objectives.
Yeah.
Okay, next slide, please.
Yeah, so this is the last case study, and it's even more challenging because of the critical application here. So this is 200 degrees C well with a depth of 6,000 meters. We are using cold tubing to log this well, given the slow speed of the cold tubing. The application is setting a plug for a further perforation operation. So the challenge here is much more bigger, slowing logging speed, deep well, ultra high temperature environment. So we have used a special 2.25 system, as Riza will highlight and comment.
Yeah, this was a first of its kind job for us, and we weren't aware of any other instances of a tool being run on cold tubing at such a temperature and down to such a depth. So we felt that we needed to prove the tool, qualify the tool ahead of the job, and to do that, we conducted an oven test, and we did that in real time mode. So the run duration was predicted to be approximately 16 hours. So we set the duration of the test accordingly. The oven was set at 232 degrees C, so higher than the expected downhole temperature, but it would give us confidence in the ability of the tool to withstand the actual temperature. So what we found during the test was across the duration of the test run, the internal temperature reached a maximum of 145 degrees C. So that was comfortably below the temperature rating of the battery as well as the electronics. So the test gave us a lot of confidence. It gave our customer the confidence to deploy the tool. The logging was conducted as planned, and good quality data was retrieved, and a positive depth correlation was conducted. The actual run duration ended up being a good 8 hours, more than the expected, so somewhere in the region of 24 hours. But despite that, the tool performed well, and the internal temperature remained below the rating of the battery as well as the electronics. So with the information we provided, the operator was able to carry out subsequent remedial interventions with a lot of confidence. That was the final slide that we had for you today. So thank you all again for joining us, and we'd be very pleased to answer any questions you may have.
Back to you, Ben.
Thank you, gentlemen. Great presentation, very informative. As they said, now is a perfect time to ask any questions that you may have. If you don't want to ask those, to the group, feel free to post them in the chat. We'll be glad to follow that chat and pass them along. The webinar has been recorded, just so you'll know. We will be posting this online in the next few days, so you'll all get a link to it. Feel free to go ahead with your questions. Let's see. Has this tool been used in geothermal wells?
Yes, yeah, absolutely. We run the same tools in geothermal wells, except for the tuning fork density. So, I mean, these tools were built initially for the geothermal industry. So it's technology that was transferred to the oil field. But we're talking about 25 plus years ago. But we do continue to use the same tools in the geothermal world.
Let's see. What are the temp limitations, and how long can this be used in the well?
Yeah. So the maximum temperature rating of the tool is 315 degrees C. So that, yeah, downhole duration, it all depends on the temperature. If we're talking about the maximum temperature rating at 315 degrees C, we're talking about a duration of around 5 hours, 5 to 6 hours downhole. I hope that answers your question.
Yeah.
You're welcome, Sam. You're welcome.
Okay, next question.
Yeah, so my contact information as well as Samir's is there, as you can see. So please feel free to shoot us emails on any queries or questions you may have. So we're located around the globe. There aren't many locations we can't mobilize equipment to. So please do come to us for any high temperature requirements you may have.
Hey Reza, I'm not sure if you mentioned it during the presentation there. When someone comes with the and uses the tools, when you get the logs back, are the logs interpreted their own location, or how does that work?
It all depends on the customer's requirements. Typically, for oil and gas operators, we would send the data to a log analyst who would be on standby to receive the data. He or she would spend a couple of hours processing that data. The data is then turned around and delivered to the customer. So it's a matter of a few hours to get the processed data and data back, and the interpretation is also dependent on the requirements and the objectives. That can take as little as 5 or 6 hours up to a few days.
Okay, thank you. Let's see. A question from Mike there says, I may have missed it, but do these tools have geological logging capabilities as well?
Only in as much as gamma ray data acquisition. I would say that's the extent of its geological logging capabilities. Yeah, you're welcome, Mike. Mm-hmm.
Just would like to mention here to the attendees that scientific drilling is capable of customizing a solution for specific applications. We do have the manufacturing capabilities, the data processing and interpretation capabilities. The all function is synchronizing together, so we can customize a solution if there is a requirement. And actually, we have done that in multiple occasions for our Qatari clients and our operations in the North Sea and in Saudi Arabia as well. So if you have special applications that such a technology is not able to address, we could talk, we could think together, and we can propose our experience and our track record to customize a specific solution for this challenge.
Yeah. So Ansar, thank you for your question regarding the high pressure scenario. Well, a couple of the case studies were in fact quite high pressure, 10 kpsi plus. That wasn't made very apparent in the case studies. I acknowledge that, but a couple of them were in fact quite high pressure.
Does that change? How does that change our approach, Reza, when they are high pressure as well, or does it?
It doesn't. At these temperatures, less than 200 degrees C, the combined impact of pressure and temperature isn't that significant. The biggest determining factor in the run duration, for example, and in the planning is the temperature rather than the pressure. But with pressure,
question.
Yeah.
Oh, go ahead. No, go ahead.
No, I was just going to add that with pressure control becomes an issue, and we can run everything on slickline or coiled tubing, so as to avoid the need for deploying electric line and with it and its associated pressure control risks.
Okay, good. And then I have an email question. Can you talk a little bit about? I mean, obviously these tools are running on lithium batteries. How do we mitigate the high temperatures with the batteries?
Yeah, so safety is a top priority for us, and lithium battery safety is up there when it comes to performing logging operations with our memory systems. So we take every precaution necessary to mitigate any potential risks to the battery from exposure to temperature, for example. So when we're planning an operation, the first thing we think about is the duration and the buildup of temperature inside the flask and its potential impact on the battery. So we have a very good safety record. We've been deploying these tools with lithium batteries for 25 plus years. So it's it's something that I feel we're very good at. Our lithium battery safety record is excellent. So it's right to be concerned about the safety factor when it comes to lithium batteries, but we do take every precaution necessary to mitigate the risks.
Perfect. Thank you. Let's see. We got questions here. Mike from Mostar Directional has asked, has the biggest challenge with the tool design been improving the insulation effect of the tool carrier or improving the robustness or durability of the electronics? Have we been more focused on the carrier or the electronics themselves?
I would say the electronics more than the insulation from the temperature. That hasn't changed a whole lot over the years. The electronics packaging has been improved. We've made incremental changes to make the electronics last longer at temperature, for example. The biggest challenge has been the ability to deploy fluid ID sensors at temperature. So for a very long time, we were running a fluid ID. The fluid ID sensor that we were running was a nuclear fluid density tool. So that used a cesium-137 source. But some 15 years ago now, we developed tuning fork technology as a substitute for the nuclear fluid density, and that has replaced that tool completely in our fleet. So that was a long-term project, developing the tuning fork density tool to withstand temperatures of up to 220 degrees C. So the next challenge is to take that rating yet higher to geothermal temperatures of 300 degrees plus. So we're a long way from achieving that objective, but it's something that we would like to achieve.
Thank you. Next question, can these tools be combined with the gyro for oriented measurements?
Yeah, interesting question, Georgie. They can, but the PLT or the caliper, that would have to be run in memory mode, of course. But it could, in principle, be deployed below the gyro, but not. But the deployment could not be in real-time mode. So only in memory mode. I'm not sure if that would be a solution to a orientated gyro measurement, but something to consider.
Okay, and speaking of, I'm sorry. Sure. Go ahead.
Sorry, Ben. I just would like to have a quick comment here on Georgie's question. There is an interesting application of combining the gyroscope with a multi-finger caliper. We call the technology DuraSet, and the DuraSet is helping actually to assess the accessibility and restriction analysis by applying a high density gyroscope readings and survey stations, so we can collect data on the micro dog legs and micro tortuosity with respect to a specific dimension for BHA, like a plug or plug setting tool or frac assembly or any assembly that can be deployed through a specific tortuosity. This will be complemented by combining the caliper with the DuraSet to identify the internal geometry of the casing, if there's a deformation, shearing, buckling, ovalization, and any of the pipe deformation analysis that we can perform. Yes, so we can combine actually the gyro with the multi-finger caliper. So yeah.
Oh, great. Thanks, Samir. Reza, you mentioned a minute ago that it would have to be in memory mode. About these tools, which ones can be run in real time?
Yeah, so the FLS 1.75 and the 2.25, they can both be run in either mode. So in terms of sensor configuration, you're talking about gamma CCR, pressure, temperature, and spinner.
Okay, great. And are these tools compatible with any other systems?
I mean, in memory mode, they can be run with any other system. So yes.
Okay. And then let's see, Mike has a question about what's the inclination limitation for the Durasat system? That's going to be based on the keeper, so.
Yeah, there is no limitation.
Yeah, well, there's no limitation from the K-STOL part. Inclination, yeah. Mike, from our gyro standpoint, with the standard keeper that we're running is about 40 degrees, 50 degrees.
Although no, I think that refers to the gyro and MWD, but the wireline conveyed gyro, yeah.
Wireline conveyed gyro, we're fine.
Yeah,
that's right.
That will work at all inclinations.
All inclinations, yep. You're exactly correct, Reza. I'm sorry about that. So yeah, Mike, to answer your question, yeah, there's nothing. Sorry, we had our last presentation was gyro MWD, and that one was still on my mind.
Yeah. Yeah, it's worth to mention to the gentleman as well that the Duraset has advanced application on assessing the multi-stage frac treatment applications. So if we are applying a frac treatment for multiple stages, so we have run caliber with client in Asia, and we have seen that a severe deformation has been resulted by the frac treatment, and actually this was restricting the deployment and accessibility of the frac assembly. So we can use the Duraset to address this tortuosity, deformation, restriction challenges, and we will advise with the output called free ID with respect to the BHA dimensions, OD length, and so on. So we can have a flexible bottom hole assembly design with respect to the wellbore geometry, because most of the clients actually are relying on the MWD data and taking the dogleg severity every 100 feet or every stand, if you would like to call it. But the Duraset is taking survey every 1 foot. So so that's a pretty highly focused survey practice, and we are zooming into each tortuosity and each torsion and bends on the wellbore. So there is advanced application as well for the Duraset. So I thought to mention if one of the attendees is facing a problem with the frac treatment and so on.
That's good, Samir. Thank you. And just to follow up, we probably will be following up in a few weeks with with another webinar that's focused on the Duraset application. So if any of you are interested, we'll definitely be able to provide more information about Duraset and give some case studies that we have along those lines and show some of the benefits of running that system. Another question here from Mike: are the systems able to run on coiled tubing drilling assembly, such as for clean out reentry run?
Unfortunately not, no. No, I don't see how we could make that work, unfortunately, no.
Reza, if you allow me, we have done something with one of the major oil field service companies who's using coiled tubing drilling. So we have we were we were being able to combine the gyro with the coiled tubing drilling for inclination azimuth purpose. But if Mike is referring to the Duraset applications and the coiled tubing drilling, that would be difficult. But for drilling purpose only, yes, we have done a couple of projects with one of the major oil field service companies to combine the gyroscope with the coiled tubing drilling assembly.
Great. It says he was wondering more about the Vulcan systems in the BHA to do a caliper log at the same time, but thank you.
Yeah.
Okay. Let's see. Any other questions coming in? Anything else from anyone?
Ben, if you allow me, I understand this presentation for high temperature, high pressure, but it's also I would like to mention to the audiences that Scientific Drilling is also offering standard production logging tools, and our standard temperature BLT system feature that it's very slim is 1.38 OD. And most of the systems in the industry is 1116. So the standard BLT system as well for standard temperature have a competitive edge compared to other system, and we have been using this for tight completion with a smaller ID completion accessories as small as 1.76 in few countries in the Middle East. So just would like to highlight that. So yeah.
Thank you, Samir. Yeah, some great opportunities there for everyone, and we'll delve more into the K-Steel Services offerings and what we can provide for you on another webinar. Let's see. Any other questions? No more questions have popped up. Give one more shot here. Any other questions for anyone? All right. I want to thank you once again for joining us today. We really appreciate your attendance, the time you invested in this webinar with us. And Reza and Samir both have their contact information on the screen. Please feel free to reach out to either of them if you have any questions about what we've discussed today. Feel free to reach out to me if we have any if there's any way that we can help. I'll make sure that someone gets in touch with you to discuss what your challenges are and how Scientific Drilling can come up with a solution for you. Thanks again, everybody. Please stay safe, and we'll see you next time.
Okay, thank you, everyone.
Yeah, thank you all. Thank you. Bye.